Good morning, everybody. I'm very glad to be here. I'm very glad that we're doing this together with PHAROS in Greece. This is the first training event that we are organizing together, and I hope we will do many of these. I was in Athens actually just the last couple of days for the Greeks in AI event, and that was great to see. Several people that are working in AI in Greece, and they're doing great things. They're creating companies and all of those things. So anyway, you can see my slides, I hope.
Yes, yes.
And so I want to talk a little bit about my presentation will be more of an overview presentation, right? So that we set the stage for the presentations that will follow that will be more specific and deep. So I want to cover more broadly things that relate with efficient training, efficient post-training, including fine-tuning, efficient inference, mostly for LLMs, but not only. Several of these things apply also to other Gen AI models. So this is the outline. We'll start with some mostly things about training the base model, and then we'll get into post-training and adaptation. We'll get into how to do attention efficiently. Quantization is a tool that you find it everywhere. And so we will spend a little bit of time on that. And then at the end, how you build not just the LLM, but the entire serving system for different types of applications. By the way, I'm assuming that if you have questions, please include them in the chat. Every now and then I will be stopping just to see if we have questions, and depending on how much time we have, of course, we may choose to answer some questions at the end. All right, so it's all about economics. It used to be about performance, how to get the best performance, but I think it gradually becomes clear that if we ignore the cost of inference, the cost of training, this will not be a viable business for anyone. This slide is maybe a year old, but basically if you're using frontier models, basically the cost for 1 million tokens is in the order of $5-6 US. And of course you can get a much lower cost, but for models that are significantly of lower performance. So there is a lot of thought that has to be spent by anyone that is building such systems about both which model to use and depending on how much money I have, basically how to optimize my system, how to optimize my inference process, or if I do some post-training, how to do that. We have to be clear about what we mean by efficiency, and of course, to measure efficiency, you need to have metrics, right? What are you trying to either optimize, or which are the metrics that you pay attention to? So for LLMs, a first metric that is very important for interactive applications like chatbots is how long does it take to see the first output token, right? And that includes something that we refer to as pre-fill. So basically, after I type my prompt and it has to be tokenized, but then it has to be processed, and that includes basically calculating keys and values and all of that for the prompt. That's the pre-fill time. It can take a significant amount of time, and that largely determines the time to first token, or TTFT. And then, of course, there is another important metric, the inter-token latency, which is the the time between successive tokens, and of course that varies. You can have a distribution, and you can focus on the tail of the distribution. But this is for interactive applications. For other applications where you care more about throughput, right? Because the application may be more like batch kind of processing. And then it's all about tokens per second, or what is the requests per second that you can serve. And of course, when you do training, there are other metrics involved, right? You have to worry about the total compute that you're burning, memory footprint. Many times you are not really limited by the actual computing resource. You are more limited by memory or communication. So we will see kind of different tricks you can do to deal with each one of those bottlenecks. Okay, so we're, after this brief introduction, we're now ready to kind of get into the training matters when it comes to training your base model, also known as pre-training. So the first thing to note is that basically you have heard about this important scaling laws, the Chinchilla paper and the results that it showed. So let me just remind you that if you have, looking at the plot at the left, if you have a specific amount of compute, let's say you have €1,000,000, and you know that with €1,000,000 you can get a certain number of GPU hours. So that is one of these curves, the amount of compute that you have. And of course, there is an optimal number of parameters for that amount of compute. Optimal in terms of minimizing the training loss, right? If you have less parameters, then basically your model cannot really achieve the loss that it's basically under-parameterized. If you have more parameters, then you don't have enough compute to actually train that model. So these are called the isoflope curves. And for each of them, if you find the minimum point, basically you have the optimal number of parameters, right, for that amount of compute. Then if you have that, you can come to the plots at the right, and for each amount of compute, right, on the x-axis, you know now what is the optimal number of parameters for your model, but also what is the optimal number of tokens that you need, your training data, basically, for the model. So that is the first important point that I want to emphasize here, that it's not only about the parameters, right? As you increase the number of parameters in your model, you have to increase the number of tokens you will train it with. And the very interesting thing is that, as you see, I mean, these points tend to be on a straight line in a log-log scale, and that's why we talk about the power laws in scaling. These things have been extremely useful so far because they allow people to kind of estimate, at least, for a given amount of compute, how many parameters they can have, how much data they need, and so on. Very important stuff. Now, the second point I want to emphasize is that the quality of the data matters greatly. So it's not just crawling the web and getting any text data we can get, because that will include a lot of duplicates, a lot of garbage. And so it's very important to filter the data, decontaminate it in some sense, make sure that it has the right mix of things that are important for you. For example, if you are building something that will be useful for coding, you will need a lot of course, coding data and so on. If you are building something that is very important to include, all languages in Europe, you will need, of course, data from all languages in Europe. And so what you see on this plot is, without getting into the details about which model this is and which benchmark this is, but the point I'm trying to make is that if you don't do anything with the training data, only some very basic filtering, you get the green curve, right? In terms of performance. And if you improve your training data set by removing duplicates, removing bad data and so on, as you see, the performance can increase actually significantly, going from, say, for example, 46 to 48%. That's considered a significant improvement in many applications. Now, the other thing, of course, after you have your data, your training data, you have to decide which architecture you will use. And of course, when it comes to LLMs, everybody these days is using transformers, not only one, but multiple transformers. But architecturally speaking, the more interesting thing these days is, of course, using mixture of experts, right? Which allows you to, even though you may have a huge model with many hundreds of billions of parameters, not all of that will be basically active for every single token that you are generating. And so, architecturally speaking, I think this is where we are right now. You need, of course, to have a router in some sense at the bottom that is deciding for each token which are the top experts, let's say K of them, that will be used for that token. And in the case, for instance, of DeepSeek v3, it has like 671 billion parameters in total, but at any point in time, only around 40 billion of those parameters are active. And you can basically do this in a couple of different ways. As you see at the top left, you have these experts that are truly, completely separate. They're not sharing anything. Or you see the picture at the right where there is actually sharing across the experts. They're sharing the self-attention layer, but then they don't share some MLPs that are further down. We will come back to a mixture of experts a bit later. Another thing that is very important, of course, when it comes to training is your memory footprint. Now, sometimes we only think of memory as something that you need to store your weights, your parameters, but that's actually quite false. You have to store, when you are doing training, you have to store gradients, you have to store optimizer states. So if you're using the Adam optimizer, you have to store things like momentum and variance, and those are typically stored in high precision. You have to store activations, because if you go back to the mathematics of backpropagation, you need to multiply activations, right, with gradients. And you may have some additional things like buffers and so on. So a trick that of course is quite standard these days, and there are libraries that can do this for you. You don't have to write the code yourself. Things like zero redundancy optimizer or FSTP. Basically, okay, what does this plot show? The plots are showing the memory footprint for each GPU that you are using for training. And the blue part is for parameters, the orange is for gradients. And as you see, the optimizer states actually take quite a bit of memory. But you can do something called sharding that you basically avoid redundancy by having each GPU only maintaining those optimizer variables or gradients or parameters that it needs at any point in time, so that you don't need to store all of those additional things that the GPU doesn't actually need at that point in time. And as you can see, you can go basically in this particular numerical example, from like a memory footprint of 120 gigabytes for every GPU to something in the order of just 2 gigabytes. Okay, that's in terms of memory, but of course, you can do many optimizations in terms of parallelism. You can, and there are different types of parallelism when you do training, right? The one that is very, let's say, simple is data parallelism, where essentially you have like you replicate the model. Each GPU that you are using is basically working on different data, training basically the same model. But you can also do things like tensor parallelism or pipeline parallelism, which are shown in these plots here. So what is that? With pipeline parallelism, basically, you kind of break your network in terms of depth, right? Maybe one transformer layer will go to one GPU, the next transformer layer will go to the other GPU, and of course, there has to be a communication overhead whenever you send something from one GPU to the next. That can create some pipeline, as we say, bubbles, right? Some wasted time. But that is very commonly done. The other form of parallelism is tensor parallelism, where you kind of split your network not in terms of depth, but in terms of width, right? So even for the same layer, I don't know, the picture is not super visible, but for the same layer, you can say split some portion of that layer in one GPU and some other portion of the layer in the other GPU. Of course, that is more tricky when it comes to the overhead that it introduces, and you have to be careful to do it only either in the same GPU or in tightly coupled, basically, GPU islands. And there are other things that you can do to increase parallelism that we can see some of them later. Another thing that is important in training is activation checkpointing and recomputation. So what's happening here is that normally when you train your neural net, you have to store the activations in the forward pass, right? Why? Because you will need those activations in the backward pass. And of course, that will increase your memory requirement. You will have to store all of those activations. So a rather standard trick that people do is that they don't store basically all the activations. They create some, let's say, checkpoints where they will actually store the activation. But then what happens, say, in this black box here is that you don't store the activations. You recompute them in the backward pass, right? And of course, that will increase the amount of computation you have to do, but it will decrease the amount of memory that you need. So these are all, rather standard trade-offs between computation and memory requirement. Now, when it comes, of course, to training, there is the question of what is the precision that you will be using. I'm sure you have seen these things before, that we're doing quantization, right? We are representing these continuous numbers with discrete values. And so there is the question of, first of all, what is the range, the maximum range that we can capture? If you go outside that range, you have like underflow or overflow, bad things. But also the gap between two successive numbers you can represent, that is the precision. You would like that gap to be as small as possible to have the highest precision. But of course, at the same time, you want to use just a few bits. It will save you both in terms of memory and compute. So what do we do in terms of training? This is a field that has advanced quite a bit, and it keeps advancing basically. Um, Maybe in the old days, you would do everything in a floating point, 32. Nowadays, every single operation, every single multiplication or summation or that happens basically in your neural net is optimized in terms of what resolution it will be using. For summations, for instance, you may want to use floating point 32 because otherwise the errors can accumulate and it can really make your training unstable. Um, and of course, what you can do, it's not just a matter of what you like, it's a matter of what the hardware that you use support, right? So each GPU these days comes with specific formats that it supports. The brain floating point 16-bit, which you see here, is a common baseline with 8 bits for exponent and how many? 7 bits for the mantissa. But there are increasingly shorter representations that are or formats that are used, such as the FP8, only 8 bits floating point, um, and sometimes even shorter than that. So I think this is probably a good point to take a brief pause and see where we are also in terms of time and in terms of questions. I'm not following actually the chat. Do we?
I have written in the chat, you may write questions there, but also you may raise your hand at Zoom and ask.
Okay. Let's proceed. So after, of course, you have your basic model trained, and in many cases, we already, we don't do that. We just use an existing open source model. Then you do your post training, right? And that's when you're kind of really creating something useful, and that's where you can create like different products and services. And of course, to do that, you need to somehow specialize your model in particular applications, right? So in the traditional approach, you would start with some prompts that maybe were written by humans together with the right response, and you would do supervised fine tuning just to make sure that your model behaves in a similar way. Then we moved to things like instead of having the humans write the responses, maybe the LLM is writing possible responses, and the human labeler ranks the responses from best to worst, and so we were training basically a reward model based on those preferences. So that's very different than the first step. Um, and of course, for some time, people were using reinforcement learning to do what's called proximal preference optimization, where you would pick a prompt, the LLM would basically generate an output. The reward model, which we mentioned before, would tell you how good that response is, would tell you the reward for that response. And you would use that to go back and optimize your policy through reinforcement learning. So that was done successfully, and it's still done. A deviation has been, direct preference optimization, sorry, which basically avoids the reinforcement learning. Now, I will not talk much about these things because they are not really the subject of the talk. The reason I mention them is that in order to do all of these things, you need, of course, training data for your post-training. And what kind of data? Where will you find this data? I mean, this is data where you need to have basically tasks, right? Together with instances or examples of those tasks. So this is also a very interesting area, how you create such data for the post-training process. You can start with some original data set that maybe was written by humans, or somehow you have some initial seed. And then you can use LLMs basically to create the task data set, right? So they create essential instructions, and then they also create the results of those tasks, the examples of those tasks, one or more. For example, give me a quote from a famous person in this topic, and the topic may be the input to this task may be that the topic is the importance of being honest, and the output is this particular topic quote that you see here from Thomas Jefferson, right? So all of this can be done basically through LLMs, but of course, what is very important is that you have the right filtering tools there and diversity checks to make sure that you will end up with a synthetic data set that is still good, right? Because if this process is left completely to run on its own, you can end up with very bad synthetic data. So, okay, suppose that you have some training data to do your post-training, then what do? You don't want to go and change your base model. It's very expensive to do that. So the standard approach for fine-tuning these days, and it has been like that for a few years, is low-rank adaptation, and also known as LoRA. And LoRa has, of course, a gazillion variations. So I'm only describing here the vanilla version of LoRa, where essentially you are adding to the output of the pre-trained model a delta, right? A small change in the weights. And that can be essentially calculated through the product of these two matrices. The idea being that they are low rank matrices, right? So you will have this parameter here called R, which determines the rank of the matrices. The premise, even though this is not like a mathematical theorem, it's more like a hypothesis. The premise is that you can represent most of the changes that you may want to do in the model very efficiently with some low rank and some low rank representation. So you don't really need, essentially what this says is that you don't need to change those weights significantly. And so this will improve both in terms of compute and in terms of memory, because you are only changing these matrices, right? We call them the adapters. Now, what happens usually in post-training is that after you have, this post-trained model, which we refer to here as the teacher model, actually you can work with that if you want, or you can try to distill it into a smaller model that is, let's call it the student model, and the idea is that the student model is trained to behave, to produce the same output as the teacher for the same input. And there are two variations of that. The kind of black box and the open or white box approach. In the white box, the idea is that we don't know only the output of the teacher, we also know some kind of internal information, for example, the logics at the output heads. and that can be very useful for training the student to behave in a similar way at the output heads. Or if it is like a black box approach, the only thing that you know is what the output of the teacher is, right? And you're training the student to behave the same way. So that can be very cost efficient because then you can take your student model, which may be much cheaper to run, and that is what you use for inference. Again, we're switching sections, so let me uh, ask whether we have any questions. Um, if not, I'll continue. So, of course, in all of these architectures, attention is the most important thing, right? And so I want to talk now about different optimizations you can do with your attention heads, either in terms of memory to improve your memory footprint or to improve your compute. Um, Now, I'm sure you know the basics at least of attention calculations, but let me just very briefly refresh your memory. Suppose that you are translating this, German phrase into the English phrase, and for each word that you produce in the English phrase, you have to basically see how it attends to all the different words or tokens in everything you have generated so far. Everything in the English phrase you have generated, as well as all the tokens in the German prompt that you received. And so, how do you calculate basically these attention weights, right? As you know, we are basically using queries, keys, and values. And the basic idea is that we take, say, n tokens that are embedded in some dimensionality d. We multiply them with these different matrices. A different one for queries, for keys, and for values. There is a multiplication here of queries times the transpose of keys, followed by softmax that gives us the attention scores. And then there is a multiplication with the corresponding vector value vectors to calculate actually the output context, which is then translated into the token that we are decoding. So of course, I'm assuming that you know these things. I'm not trying to get into the details here, but as you understand, these calculations can take some time, and also storing these matrices can be significant in terms of memory footprint. So the first thing we can do is to try to optimize basically in terms of how much time we will need for moving this data between the GPU and yeah, to basically reduce the memory bottleneck. So one approach that is used often is called flash attention, which is a name that I don't think is a very good name. Anyway, it exploits the memory hierarchy in a GPU, right? So in a GPU, typically you have a little bit of SRAM, which is very fast, but it may be in the order of just, say 20 megabytes. And you have the HBM, the high bandwidth memory in the GPU, much bigger, but lower bandwidth. And you have, of course, the main memory in the CPU, which is much lower, and the bandwidth is orders of magnitude lower. So you can spend a lot of time just moving data in and out without actually the GPU doing anything useful. even though you bought these very expensive GPUs, maybe they are most of the time idle. The flash attention idea is that we will try basically to do most of the work in the SRAM of the GPU by basically copying in that small memory, not the entire keys or values, but essentially. So essentially, what I'm trying to say is that if I go to the previous picture, we don't really calculate this entire matrix um, in the GPU SRAM because it will not fit. We just calculate blocks of that matrix in the SRAM. And we do that by kind of being intelligent in which parts of the queries and which parts of the keys we are transferring into the SRAM before we actually output the results to the HPM. So it's just a matter of reducing the memory bottleneck by being very careful about which specific data you are moving into the small high bandwidth memory that you have. Now, this doesn't do, of course, anything to reduce the the storing the amount of memory that you need to store the keys and the values. So let's talk now about the KV cache, right? The key value cache, which is one of the most important building blocks these days in all LLMs. If you wouldn't do caching, right, for every decoding step, you would have to recompute basically all the previous keys and values. I'm not saying queries because basically the query is not something that you can reuse. It's only used for that particular token. But as you see from this second equation, actually, this shows it quite clearly. Uh, when you are at step T, right, of course, you need the query vector for that step, but you also need the previous keys and the previous values, right? So instead of recomputing them all the time, which would give us a quadratic overhead with a sequence length, with T in other words, the idea is, can we actually use caching, right? Can we compute these keys and values once and hopefully reuse them again and again in the future, right? And that will basically take that quadratic cost down to linear cost, linear with a sequence length. But of course, it will reduce your computing time, but it will introduce a memory overhead that will be growing linearly if you want to store all of these previous keys and values. So an important thing to remember is that if you just do things in the vanilla way, the way that it's written on this slide, you will need a KV cache that basically is the size of that cache is proportional to all of these things that you see here, right? What is your context length, which is essentially T, how many layers you have in your LLM, how many KV heads you have, because you may have multiple attention heads, the dimensionality of the embedding of each head, and so on. So even the KV cache can be quite large. Actually, in some systems, it can be larger than the amount of memory that you need for storing weights. So as I just mentioned, the typical LLMs, they don't have only one attention head, they have multiple attention heads, let's say 8 of them. And so the very brute force way of doing things is to have essentially separate keys and key and value heads for each of these attention heads, right? but that would, as we see in the previous formula, that would increase the amount of memory that you need for the KV cache proportionally to the number of heads that you have. So there has been a lot of innovation on how you can optimize that. There is something called grouped query attention, or GQA, and the idea is that instead of having, separate keys and values for each attention head, you are basically sharing, right, the same key and value heads for multiple query heads, and so you don't really have to have, and the extreme could be that you have only one, essentially, key and value head for all the query heads. So going in the previous picture, the extreme would be that even though you have multiple attention heads, all of them share only one key and value head. And that would, as you see on the picture here on the left, significantly reduces the requirement, the size of the KV cache, right? In this case, from, let's say, more than 50 gigabytes down to just 235 gigabytes. So that's one trick. Another trick, which is used by DeepSeek version 3, R1, is to do something called multi-head latent attention. So this is not just reducing the size of the KV cache by sharing key and value heads. This is also compressing the what you actually store in the cache. So instead of storing the actual keys and values, you are basically storing some kind of latent representation, some compressed version of those vectors. Of course, that increases the complexity, both of training this network and during inference. But it can also have significant benefits in terms of the size of your KV cache. All right, we're switching to another section. So again, let me ask if there is anything in terms of questions. If not, let me get into compression and quantization. So when you are deploying such systems, again, quantization allows us to basically represent numbers with a smaller number of bits, and you can apply this trick in pretty much everything, right? You can apply it in weights, you can apply it in activations, you can apply it in the KV cache itself. So it's a very powerful tool. Let's see how you can use quantization in the case of the weights. So after you have trained your model, post-training, the question is how you can represent your weights in a more efficient way. And there are different ways to do that. I will mostly talk about something called AWQ, Activation Aware Weight Quantization. So first, let's see, if you don't do anything smart, if these are your weights in floating point 16, right, and you simply truncate them and compress them using an integer 3 format, which represents any number from -4 to +3, then of course, as you see, you lose a lot of information about the weights, right? And you end up with a post-trained model that is very bad. This perplexity number that you see here in red, the higher it is, the worse the model is, basically. So another approach would be to basically ask, okay, which of these weights actually matter? Maybe for those weights, I would have a higher precision. And which are the weights that matter? Remember that when we do our our forward pass, basically, we multiply weights with activations. So maybe here what I have as X is the activations, and you see, with different colors, I represent how big the activations are. So here in this column, I have a very strong activation, right, which can happen quite a bit especially in LLMs. Maybe for those corresponding weights, I can use a higher precision format, right, such as FP16. Well, that sounds good in theory, but in practice, it may be difficult actually to represent some weights in high precision, some other weights in low precision. Right, the hardware will not really let you do that kind of thing. So with activation aware weight quantization with AWQ, what you do is you have the same precision, the same format for all the quantized weights, for example, in 3, but you are playing with the math essentially. You are scaling the activations down by a certain factor, let's say alpha, right? How big this factor is depends on the statistics of the activations. You can calculate the statistics of your activations to find the value of alpha. So you are scaling down your activations, and at the same time, you're scaling up your weights, or the other way around. And and that essentially will still give you the same mathematical result, but it solves the problem that I mentioned before, that you have to represent different weights with different uh, uh, different formats. So this is quite commonly done post-training, of course, the quantization of the weights. You can also try to do quantization of the activations and the weights, not only the weights, right? But here we have a harder problem. The activations quite often they involve some outliers, right? Some values that are very large. And that is something that you don't want to miss. I mean, if you truncate those outliers, essentially your LLM will give you the wrong answer. These outliers may be, some, for instance, tokens that have much larger probability than others. So you want to maintain these outliers, but the outliers are giving you a hard time with the quantization, because if you look at this picture here, um, you need to capture the outlier with this quantization value, which means that all these other quantization levels are not used by anything, because you don't have any values in that range, right? And then all these lower values, which are more typical, will get quantized basically at the same quantization level. Um, so how to deal with that? And this is what this method called smooth quantization. This is what it does. Again, it's based on a mathematical trick, right? It will basically adjust both the activations and the weights, so that when you multiply again weight and activation, you are getting still the same mathematical result. But essentially, the way it works is that you are scaling, as you see here, you are scaling the activation. So this big outlier now appears as smaller compared to the typical values. You are doing the scaling, and you are doing essentially the inverse scaling with the weights. And that allows you to quantize the activations more effectively. Another common quantization is in the cache itself, the KV cache. Basically, as we said before, during autoregressive decoding, during inference, the KV cache size will grow with the size of the context. And so one thing you could do is do quantization of the values that you store in the cache, that you store in the keys and the values. Now, there is an interesting thing here. Quantization error in the keys has a different effect than the quantization error in the values. Why is that? Remember, the keys, we multiply them, of course, with queries, and then we do a softmax, right? Now, remember the mathematical formula for softmax with those exponentials, right? If you have a small, even a small quantization error in some of these key vectors, because of the softmax, it can actually explode. It can become much larger. This is not, of course, the situation with the value vectors. You don't have a softmax in that case. So we have to take this into account. We have to consider the effect of the softmax on the magnitude of the quantization errors. And this is exactly what this method is doing, quality adaptive quantization. It's a method that applies only to KV cache. And essentially, by considering how softmax works, it makes sure that the values that are kind of sensitive, are outliers, may be represented in higher precision, and other values that will not matter much are stored in much lower precision. Let me see. We are close to the end. We're running out of time. So I will probably not have time to talk about this section, which is about the serving systems, right? As I was saying before, just having the LLM is not necessarily your product. You will build an entire system around the LLM, which will be, scheduling how different requests are run, and you can have like a RAG system. Retrieval augmented generation, where you store a lot of additional documents that may be needed. So let me just very briefly show you the slides without really saying much. When you are building such systems, there is the question of batching, right? So you can have different users that are basically sending requests to the same model. And you want to make sure that your GPUs do not stay idle. So you can think about how to batch these different requests so that the GPUs are busy all the time. But of course, you don't want to create any interference between different prompts, between different requests, which is fine. You can do that because you are using those masking matrices, right? When you do decoding. So that's one area of activity. Another one is that in many of these applications, they tend to send basically the same, essentially the initial part of the prefix of the prompt may be the same, the prefix may be the same, and so you can also cache entire prompts and the responses that you give to those prompts. There is the notion of speculative decoding, where you have a smaller model that we refer to as the draft model, that you can use to generate a lot of cheap responses to a particular prompt. And then the target model doesn't have to do as much work anymore, because it doesn't really have to produce a response token by token. It has to essentially evaluate these cheaper responses that it gets from the draft model, choose maybe which one to use, and maybe for tokens that they don't get a sufficiently high score to just generate those tokens through the target model. RAGs, I'm assuming that most of you know how they work, right? So the important thing there is to be able to choose from the different documents that we have embedded, which are the most relevant parts to a query, and only those relevant parts will go into your prompt. And another thing you can do when you are building such systems is, instead of only relying on one model, which may be the most expensive model, the best model, you can have also other models that you can use. And so when you receive a request from a client, the question is, okay, which model will I route it to? I would like ideally to route it to the cheapest possible model that will still give me good results, which of course is a very hard thing to know. But there are heuristics and tricks that you can build into this router so that it knows which model to choose for its request. So I'm closing. I want to basically say that this is an area where how to think about these things. It's not just a collection of tricks, right? We have to think about the end-to-end system that you are building. Instead of only thinking about performance, you have to think about cost. You have to think about where your bottlenecks are, right? Are you bottlenecked by memory, by compute? Do you care about throughput? Do you care about latency? Do you really care about performance, or even a medium performance can be fine? So, and then if it's clear, like what is your bottleneck, right? Memory, latency, training cost, and so on, there are a number of different mechanisms, levers that you can use, and in many cases these are trade-offs, right? So maybe I can do something to reduce my memory, but that may hurt me in terms of compute, or maybe I can decrease my training cost, but that may also decrease my performance. So a lot of this, to be honest with you, I think is more like art rather than a science, but it's also very, very interesting. So I see that we're past the time that we had, so let me stop here and ask if there are questions. Hopefully there are some questions.
There are 3 questions, yes.
Okay. And if I don't know how much time
Yes.
can we have
Okay.
for it.
Yes, we can spend some time on the Q&A, of course. And thank you
Okay.
very much for the comprehensive overview of efficient training.
Yeah, I
Uh,
mean the goal was to exactly as you said. I mean the goal was to have like an overview kind of presentation, of course, covering many different things, but hopefully they set the stage for what will follow in the subsequent presentations.
yes,
So
exactly.
let me just read the questions. Can you please explain how exactly DeepSeek developers used O3 distillation, probably black box, to replicate its performance? They were and still are accused of using distillation to replicate performance. And are there countermeasures against model distillation? This is a very good question, but I will disappoint you. I don't know the answer actually. Especially the countermeasures for model distillation. I mean, how would you do it? I'm sure many companies would like to have these kind of countermeasures because, okay, when using GQA with a single KV per cert across all query heads, is it equivalent to the single head attention implementation? Or do we still learn separate query projection matrices? Okay, so I think I can answer this one. So No, it's not equivalent. I mean, you're still getting a benefit because you have these different queries, right? Query vectors. So you are getting a benefit. It's not like just using a single head, a single attention head. How does PTQ compare to LoRa in terms of inference accuracy? That's a very good question. Are there any hooks proxies to tell us what is better in which case? Can we mix LoRa and PTQ in different layers blocks? Yes. Yeah, I don't think of LoRa and PTQ actually as two competing things. I mean, you can use both of them. For, depending, of course, on how strict your memory footprint is. Why are keys quantized per channel while values are quantized per token? And also, what factors determine the lowest bit width that can be used for KV cache quantization before the model accuracy significantly degrades? Yeah, that's a great question. So the difference between how you quantize keys and values, I think, has to do with what I was discussing about that keys will go through the softmax, and so you can have basically the issue with the quantization errors being essentially affected by the softmax. I think. What factors determine the lowest bit width? Right. So, I mean, again, it has to do with the yeah. I mean, it's hard to answer this question without talking about a specific system, right? Everything else that affects the KV cache. I mean, if you go too low, say integer 4, right? I mean, I believe that it can affect your accuracy very much, but it also depends on everything else that you are doing, such as how many attention heads do you have, and sorry, some of these questions are too hard, I think, for me, but they're very good questions.
I
Thank you.
think, like you said, Constantine, it is more of an art than a science many times because a lot of parameters are involved and methods and also libraries, how all these are implemented in actual libraries and frameworks. So I believe there
Exactly.
is no yes or no answer in all of the questions or straightforward answer. We need to do experiments, and from my experience, it depends on the problem, on the data set you have, and on the compute you have, etc.
Yeah. Okay, I see that we are already 10 minutes past
We
the
have
time, so I don't know if
another question as well.
okay, let's look at that. When integrating dynamic RAG with formal ontologies, right? How do you reconcile the problem of ontological drift? What is a good architecture to prevent semantic routing decay? I mean, that's an excellent question. I don't know if I'm not able to answer it. I don't know if somebody else has worked with this setting of having both, a formal ontology and also using RAGs. I mean, I can see what the problem is, but I don't know if there are any solutions actually.
Okay, thank you very much one more time, Constantine.
Thank you, everybody. Oh, I'm sorry. I'm very sorry. I forgot to show you maybe the most important slide, which is this one. And please give us feedback. Use this QR code It's the first training event that we do through PHAROS Cyprus. Certainly, we can become much better. So please give us feedback. Yeah, thank you very much.